Good afternoon. Our project is the Integrated Light Circuit, or DMD. It's a UTDesign project sponsored by Texas Instruments, and group members include myself, Joshua Elander, computer engineer, Ricardo Gregrod, who's a CE doubly, Zachary Hines, who's a CE, and Dale, who's a CE doubly. So TI tasked us with designing this integrated light sensing circuit for their digital micromirror device. The DMD is part of Texas Instruments' digital light processing technology, which can be found in most projectors or movie theaters through the US and the world. And how it works is lights are shown upon these little mirrors on the device that can be set to either 0 or 1, and by cycling through red, blue, and green lights, they will then create an image. What our project needs to do is create a circuit which will sit on the DMD, will monitor the amount of light that hits the device, and send this to the light controller, which can then increase the system controllability. The challenge is that because our device, our circuit, needs to be exposed and on the DMD itself, it's not enclosed by the light shield, and it thus be a detriment to the performance. So the goals we went about in approaching this project were we first wanted to learn more about the DMD and the DLP technology and how it worked. We also wanted to find a reliable way of getting the light onto the device while measuring the transistors in order to create a circuit that would take in this and be able to send that to the light controller. Our approach to this was we first researched the device in general and looked into ways to make circuitry that would sense the light. We also then learned more about the device by running characterization sweeps using a coding station and a Keithley 4200. Next, we had to find a light source and figure out a way to get that light source onto the device while running these tests. So what we did was we borrowed a strong LED from Texas Instruments, and we had it run through the microscope of the probing station onto the device. And we were able to measure the wattage applied per area by using a thermopile and calipers. These tests were helpful in figuring out how to design our circuit and measuring, but ultimately we were still looking at more reliable and better ways of getting the light onto the device. So finally, we also have looked at rough designs of what the circuit's going to be like. So we are thinking about using the pre-existing pond of mirror pixels with the bit line going down into an ADC, which will then output this data into the light controller. This should be able to let them control how much light, if it needs to increase or decrease, is hitting the device. In conclusion, we successfully characterized the transistors, and which will help us design our circuit. We're able to simulate the device, and through future testing, we'll be able to complete our finalized version. So now, questions?
What's the required sample rate on your ADC?
We don't have a specification for that as of yet, but we're still looking into how we're going to output this. We're pretty sure we're going to be outputting our information from the ADC digitally, serially. So it'll be 2 bits and we'll be sending out serially by with some shifting or some sort of. That part of the circuit is still in development. We haven't exactly. We've been more into characterizing what we're actually getting from the content.
Yeah, this first semester we've been doing research and testing, and then the next second semester is focused on the circuit design.
Can you elaborate on what kind of light source you have used?
We just have it's a strong LED. It's like 600 milliwatts. Yeah.
So we're getting about 600 milliwatts through the microscope onto the device itself. That's losses through the microscope and through the microscope that we're using to route it through. So we're looking at other ways of getting the light more reliably and stronger so we can get a better reading from the device.
Stronger, that's The measurement